a thunderstorm event on Christmas night for those who are outside on that night. And this presentation just covers some work that Valentine, Alain, Rob and myself have put together on this event, and a little video from David too. So let's begin. So we're going to first go through the events of the day, and the best place to start was probably Christmas lunch.
Oh, yes.
And shortly after Christmas lunch, we had Rob presenting his seminar. And he put up a satellite image which looked a little bit like this. So this was Christmas Day. Shortly after lunch, you can see the whole northwest of the continent is pretty much cloud-free, which is actually a good thing for storms. So it's currently baking in the sun at the moment, and you'd have temperatures to the mid-40s across the Kimberley region. And on this day, for those who don't remember, we were coming down from the north into Broome for the evening. So the day evolved reasonably quickly after lunch. So within 5 hours, we had widespread convective clouds across the top end, including one moving across the Kimberley region there, which is the thunderstorm we're going to be talking about today. You can see it developing into the evening there. So, looking at the Kimberley region itself, with looking at a lightning climatology. So this was reconstructed from a satellite-based sensor. You can see we have our global hotspots, Colombia, Congo, up around the Himalayas. But within Australia itself, we have our own little hotspot, and it's centered around the Kimberleys. It's particularly around the Derby region, King Sound, which we went across just before we crossed into Broome. So this is a particularly active area for thunderstorms. However, as we'll see, not a lot of work has been done in this region before. So just a bit of background on the region itself. So this is that sound I was talking about with Derby down here. We were crossing down to Broome, down the corner here. So you can imagine this region, it's particularly arid through the summer before we have the monsoons arrive. So it's baking to the mid-40s. You have also strong sea breezes coming in along the coasts. And one process we know that occurs here quite regularly is with this intense build-up of this continental heat, we have a heat low establishing across the Kimberley. And a heat low increases convergence from the coasts into this region and acts as a mechanism for triggering thunderstorms, which is probably what happened on that day. However, looking through the literature, there's actually no studies which exist on thunderstorm systems through this region of Australia, because we've never had a research-grade radar out here before, or a field campaign. However, there are some studies of cloud lines which propagate off the Kimberley region or off the Pilbara region, similar to what we get off Cape York, so there are morning glory clouds. Back in October, we had one of those clouds which was observed. This is from satellite, looking at a combination of water vapor channels and visible imagery. I'll just let the loop play, and the crosses on top are our lightning detection from weather zone. You can see thunderstorms just to the southeast of Broome when the loop restarts. So these thunderstorms, as they develop around this region here, so this is more Pilbara, they're actually generating these wave clouds which are propagating out, Coriolis forces acting upon them, and they're starting to rotate. This whole air mass is starting to rotate down to the south, where it's triggering more storms through the Exmouth region later in the day. So these features have been documented from satellite studies before, but this is the first time we've actually had a research-grade radar moving through the region where we can study these thunderstorms and the processes triggering these wave clouds. And you can see these wave clouds are almost up towards East Timor as well. So these wave clouds could propagate into the maritime continent, East Timor, Indonesia, and they could continue triggering convection up through those regions as well. So the first data set we're going to look at is our radio soundings. So for those who haven't done it yet, it's simply a balloon with a small weather station attached that transmits the data back as it ascends through to about 30 kilometers, 25, 30 kilometers. So the radio sounding for that afternoon for that early evening, is plotted on the right. And we can see we're particularly interested close to the ground. So this is the lower 4 kilometres here. Very close to the surface, if you can remember from Rob's talk, we have 2 pieces of information here. We have on the left, we have the dew point temperature with height, and the air temperature, the ambient temperature with height as well. You can see close to the surface, these 2 lines are very close together. That's indicating a very high humidity. So this is our maritime air, which is evaporating off the sea surface or through sea spray itself. So it's contributing to an almost saturated layer here, and then directly above it you can see these lines diverge and they stay a considerable distance apart until we get up towards our 4 or 5 kilometre mark. And this is actually a land air mass sitting on top of our maritime air mass. To a meteorologist, this sounding looks really weird because we're not used to seeing such an extremely moist, humid environment, very shallow, with almost like a desert environment sitting on top of it. And what the implications are of this setup for thunderstorms is a little bit unknown to us as well, because thunderstorms will either be developing off, you can see there's more moisture up here, they could be developing off this layer here, or if they're capable, they could be tapping into this more extreme moisture at the surface. And that was one of the questions for us on that evening. On top of that as well, you can see right through our wind profile up to about 15 kilometres, we've got these easterly winds, very persistent. So these winds are also important for helping storms to organise and strengthen as they propagate out to shore. So this sounding, for us, we wouldn't be able to determine that there would be a storm over the ship, but we can see the environment has got good wind shear and there is some moisture present. However, there is a lot of inhibition. So Rob mentioned when he put the balls on Alain's head on the Christmas Day talk, that process which is preventing the instability from being released is particularly strong in the sounding due to that very dry layer above the surface. So looking now at some more satellite data from Imagery 8, which is a Japanese satellite we use for weather imagery centered over the Pacific maritime region. So this is, first off, I'll show you some long-wave infrared imagery which has been enhanced. So the colours in this actually relate to the temperature at the top of the clouds. So our greens, yellows through to reds are our minus 50, minus 60, minus 70 degrees. So you can see our thunderstorm initiated just up from King Sound, a little bit further inland. From there, it continued to grow quite rapidly upscale. You can see we're having cloud top temperatures in there of minus 85 degrees. There's also a couple systems here. You can see there's a couple lobes. So there's separate thunderstorms here which are interacting with each other. But this upscale growth continues as it propagates towards the Broome region. However, you see the thunderstorm as it approaches Broome looks much weaker, so the colours have gone from this 70 degrees down to, as it moves offshore, down to much warmer temperatures, so minus 50, minus 60, and this is indicating to us the thunderstorm's weakening as it moves offshore. So inland it wouldn't have had any of that more complex environment which we see offshore with the shallow maritime layer and the more desert arid layer on top. Inland where it developed, it would have just been more of a desert environment. So these storms would have been developing off moisture that's been lifted up 4 kilometres or so. And at that point we start to see convective clouds form. So this transition from a desert environment to more maritime environment was of particular interest for us when we were up off Darwin as well, trying to determine what processes allow thunderstorms to survive this transition. So as the thunderstorm transitions offshore, you can see it, even though it weakens, there's still some convective processes going on, some clouds still present, and you're starting to see this ring form along the edge as well. So even in the last couple frames, when the thunderstorm is almost completely dissipated, you can start to see the air mass of the thunderstorm, or potentially any gravity waves that's generated in the boundary layer, are still propagating away from the storm into our Timor Sea. And this last image here is from the shortwave infrared channel, which allows us to pick out clouds better against the sea or land background. And you can see there are actually these wave clouds. There's multiple wave clouds in both the northern and in the western region of the storm. So these are those boundaries which are propagating across our Timor Sea towards the maritime continent up north. So visually, we were out there with lightning and the wind, and we could see this faint roll cloud coming towards us, those wave clouds which I showed in the previous imagery. That was the best image we got of it. Mahesh got that for us. But if it was daytime, it probably looks something more like this. So this is a morning glory cloud over Burketown in Queensland. So this is essentially, if we look at some concept diagrams, we have our thunderstorm cell. It's producing all the dense cold air with precipitation that's rushing out in front of it. And this process where it encounters the air ahead of the thunderstorm, this is our gust front. So this is where you get your first strong shift in winds, the first bit of rain before the main thunderstorm arrives. And this thunderstorm, we know the gust fronts on these Kimberley storms can be very intense because you have all this dry air sitting above where the rain is evaporating as it falls through, and that continues to cool, make this air coming down more dense and deepens the gust front and accelerates it. So it's pushing off from the thunderstorm, and looking at the diagram on the right, as our gust front pushes forward, it's also lifting air ahead of it. So it's lifting, in this case it would have been lifting the maritime air we saw, all that humidity in it, and the dry air from the inland boundary layer as well. So from this, we'd expect to see more of a pressure drop at this point. So we have our thunderstorm winds meeting the winds coming in this case from the coast, and also a stagnation. So the winds will drop off and the pressure will start dropping as well. So if conditions are right, these gust fronts can also trigger waves in stable layers of the atmosphere itself. So these waves, it's almost like you're pushing against, if you've got your hands in a bucket of water and you push against it, and when you stop your hands, you'll see waves propagating away from it. And it's a similar process in the atmosphere as well. We have various layers of density and a stable layer between, and you'll get waves propagating off them. And these waves are what generates those clouds which we saw in the previous satellite imagery. So now just a quick video from David. I don't know if we have sound on here, but we probably don't. Actually better just double check. See how loud it is.
Tell us what's happening.
So at this point in time, we're starting to see winds around the 30, 35 knot mark, 70 k's per hour, push through. And we're all starting to get a bit excited because we couldn't actually see. Usually we're used to looking at our Doppler radar imagery and having an estimate of what the wind speed would be coming towards us. But in this case, with the Doppler radar, the radar on the roof wasn't actually able to resolve those winds because there wasn't enough precipitation suspended in them, or particles. So it was a bit of an unknown of what was going to hit us at that point.
70 kilometre per hour winds. Yeah. So you're pretty happy with this?
Yeah,
Your storm chasing?
Stand over here.
Sorry?
I'm struggling to stand over here.
Keep going with the warm up.
So around this.
This is the storm chasing too. The ocean.
So the winds are starting to pick up now, so they're picking up to around 45, 50 knots. So at this point we're starting to hold on to things. It's getting a bit too windy to be out there. And we had to call it quits and come inside shortly. Couldn't even hear you, David. So we're back in on the bridge now. And we're just having a look at the thunderstorm outside.
We're just collecting radar measurements while we're stationary.
Yeah.
So I think our plan is to start a little bit longer maybe. It's rain about.
Yeah.
Not much.
So you can see from here as well that the clouds at which this lightning is moving away from, just place.
So maybe it's rain about.
Yeah.
Not much.
I was just moving.
That's the negative from us. And we'll do the same thing at the other radar sites too, so I'll
Yeah, so we're actually be able to see a lot of the lightning strikes. There wasn't a lot of rain around us, and the cloud bases were also very high, which relates to that dry air which is sitting just above us. So it's a spectacular view of lightning on that night.
Yeah.
So there you can see some crawlers moving across underneath the storm, and eventually all our instruments were taken out too on that night. So now to look at some more data from the ship. So the first 3 data sets we're going to look at, as one is going to be from the Met station on the mast. So the mast has got a port and starboard Met stations on top, and we were using the port in this case because the thunderstorm was coming from the port side. Ocean Pole, our C-band research radar on top of the Monkey Island, and also a LiDAR, which is essentially a laser which we use to measure aerosols in the atmosphere. And this is within the container on the bow as well. So using these 3 instruments, we can use the radar to look at the precipitation, the rain coming towards us. We can use the LiDAR to look at the aerosols within the atmosphere, which gives us an understanding of how deep this maritime layer was, this very shallow moisture layer. And we have our weather station as well, which gives us our temperature, dew point, pressure, wind speed, and wind direction. And this all relates to these processes of the gust front and potentially gravity waves coming off the thunderstorm. So I've actually got some indicators here as well. You can see everything's centered on the radar. So this is the 11 UTC radar scan. The LiDAR is a vertical profiler, so it's essentially, we have to plot it with height against time. And I've got a red dashed line of which step we're looking at in corresponding with the radar data. And I've also got a red dot on the weather station data to indicate where we are in the time series as we move forward with the radar data. So a few things start to happen. You can see this yellow line running through here. This is the top of our very shallow maritime boundary layer with all that moisture and aerosols in it. And it gives us an indicator of how it starts to change before our thunderstorm hits, where we can see the signal gets more saturated over on the right hand side. First, there's a bit of a wave feature developing in the boundary layer, and we can see that in the pressure trace as well. So these are potentially very shallow gravity waves coming off our thunderstorm, propagating ahead of it. And there's a couple there. You can see some more wave-like disturbances ahead of our thunderstorm. You can see the waves in the pressure trace as well as our thunderstorm begins to approach. So at around 12:30 UTC, you can see our pressure starts to increase rapidly. So this is about 4 millibars in 10 minutes or so. And at this point in time, we also see our wind speed drop off, so we're entering that stagnation zone, and our wind direction shift from our southwesterlies around to our easterlies from the coast. So this is our thunderstorm air mass moving in. So you can see the storm itself is also just positioned on our port side coming across. So you can see as it comes over, we have our pressure rapidly increase. Our wind speed, this is the first increase in wind speed to around 35 knots. And then we can also see our second increase where we get to around 50 knots. We start to see more of this the air mass change. So we can see in the temperature trace, which is green, temperature drops rapidly, humidity drops. At the radar on the roof here, we've zoomed in, and this ring around the radar here, which is centered on the red dot, is the 25-kilometer range ring. So you can see as the thunderstorm moves through, you can also see there's some more, if you look very carefully, there are some linear features along the edge here, some lines, and these might be associated again with potentially our gust front lifting a cloud ahead of it, which we saw visually. And it continues to propagate away. We also have another instrument as well in the container on the front. It's a different kind of radar to what's on the up on the Monkey Island. And this type of radar is much higher frequency. So Basta radar is up here on the right. And the high frequency allows us to measure cloud droplets rather than rain droplets and precipitation. So it provides us an indication of what the cloud density is and also Doppler velocities as well, so vertical wings. This is a profile again, it's a vertically pointing instrument. So we have height up to 15 kilometers and our time in UTC. And you can see our thunderstorm as it starts to come across the radar itself. We see initially it's very shallow and it continues to deepen as it moves across. And it's quite elevated to begin with as well, which is likely relating to that very dry air mass sitting across us. You can see as well we have these sort of, the cloud field and within the radar is sort of slanted as well, and that's indicating we probably have very strong winds pushing our precipitation and very small droplets towards the ship at the surface. So that's those strong easterlies we saw. And then we can see the evolution of the cloud later in the evening. We go from the leading cloud, which is a bit shallower, to our deeper convective clouds, and then later on in the evening we have our trailing cirrus clouds from the anvil. So this is the mushroom part of the cloud. On top we have these spreading high-level clouds, and you often see lightning activity under these as well, particularly in this part of the storm. Potentially some armadas there as well. So those bubbly clouds you see from underneath the thunderstorm anvils, this is probably these features here underneath the anvil. Yeah, so we couldn't see it visually. So just some questions for us. We just put this together quite quickly, but some bigger questions for us to maybe come back to this region one day is what the thunderstorms in the Kimberley are particularly impressive because they get to such a large scale, but we don't have a good understanding of what drives this growth to these scales at the moment, besides just the Kimberley heat low being present. How frequently are these gravity waves occurring off the Kimberley is another question. How far are they going? How quickly are they dissipating in other cases? So there's some questions we'd like to come back and have a look at in the future. And finally, what we're also doing as we move down the coast is we're calibrating our land radars with Ocean Pole as well. So Valentin prepared this plot. I'll just talk you through it quite quickly. So we have this scatter plot here, shows us the reflectivity from, in this case, the Broome radar as we pass Broome and we're observing all those thunderstorms we just looked at, how the samples from the Broome radar compare with Ocean Pole, which is the radar on the ship. And you can see that there is some bias towards lower reflectivities on land. In particular, you can see that if it was a one-to-one relationship and the radars were both, if the Broome radar was perfectly calibrated to Ocean Pole radar, we'd expect it to be sitting across this line. But in fact what we find when we have a look at the distributions is there's an offset of around 2.5 dB. And when we apply this offset, we can see that the distribution sits much closer to the relationship we'd expect for a calibrated radar. However, Ocean Pole itself is only a reference point for the calibration. It's not an absolute calibration. So we're ongoing work as well to try and calibrate Ocean Pole. And we're continuing this. We've done this at Port Hedland as well. We have some samples which you just picked up around Exmouth. And we've just arrived at Carnarvon as well. So we'll be continuing this work, collecting it collecting these data sets when precipitation is present so we can calibrate our land radars against our ship radar. Cool. Any questions?
Impressive data.
Yeah, it's
Yeah.
a hell of a lot to go through.
Yeah.
So we're still just scraping what we can do with it at the moment after a couple of days.
Those semicircular wave fronts, how fast were they propagating out to sea?
The phase speed of them, I didn't get to measure them, but they generally propagate considerably faster than the gust front itself. So you can, the thunderstorms on that day were moving towards us at about 50, 60 kilometers per hour. So they're maybe upwards of 100 kilometers per hour. And that relates to the properties of the stable layer from the atmosphere, how deep it is.
Yeah.
Its phase speed through that. So that's another thing we need to look at. Yeah.
I'm not familiar with that kind of gravity wave that you're talking about there. Are they propagating horizontally or?
Yeah, so the ones which we were looking at are relatively shallow gravity waves which are trapped within the stable layer of the atmosphere. So, and they're propagating horizontally. There are other types of gravity waves which can be through the full troposphere, which can be triggered by thunderstorms. And you can also get gravity waves triggered by such as sea breeze collisions as well. Got two currents.
What is exactly triggering this one?
So the gust front, so the strong winds propagating out of the thunderstorm and colliding with the onshore flow, which was occurring that night. So you have these two air masses colliding, and there's likely a stable layer there as well. And as it collides and pushes through the stable layer, it sets off gravity waves.
So the phase is sideways, but the motion is mostly vertical with the motion of the
The motion is vertical
outwards.
through it, and yeah, the phase is horizontally.
Yeah.
Yep.
Nice.
Any questions?
Just looked a bit like the ocean, but up there.
It's all yeah. It's all inverted, right?
So when you plot those vertical graphs from the cloud precipitation
Yep.
laser machine,
Yeah.
you can identify the cloud types from that graph, or was it because you knew what kind of clouds were present?
We were identifying them by their altitude.
Okay.
So we know cloud types occur at specific altitudes. So we can also use our research radar on the Investigator to look at different precipitation types. So it can tell us if it's snow, large droplets, little droplets, various properties like that. And then we can infer information about the microphysics as well.
Cool.
Is this because it's the dual polarizing radar